Hi all, welcome to fifth video session of color image processing. Today we are going to cover shift steps to compute a continuous wavelet transform, scale and frequency, continuous wavelet analysis, and we will discuss MCQ. Shift for wavelet function phi of t. This is a shifted wavelet function of phi of t minus t. This is phi of t starting with 0. Wavelet function phi of t. This is shifted wavelet function phi of t minus k. Shifted phi of t minus k. Steps to compute a continuous wavelet transform. Take a wavelet and calculate its similarity to the original signal. So this is the signal. This is a wavelet function. So we have to calculate the similarity to the original function. C is equal to 0.0102. Shift the wavelet and repeat. Then again you shift it and repeat the same thing. Again you calculate the similarity. Step 2. Compute the continuous wavelet transform. Scale the wavelet and compute it. Scale it. The constant is 0.2247. This is a low scale, a rapid change, high frequency. This is a signal. Wavelet, this is high scale, slow change, low frequency. Low scale, rapid change, high frequency. This is a signal. See here. Rapid changes and high frequency. And here we have a low scale. Here signal, slow change. You can observe here. And frequencies are low. Wavelet, slow change and low frequency. The scale is high. Scale and frequency. Continuous wavelet analysis. We can use MATLAB to analyze the continuous wavelet function. So use the command, MATLAB command, wave menu is equal to continuous wavelet 1 to t. File is equal to load signal. From the toolbox, you can load this. db4 scale 1:48. Zooming details. You can get the wavelet here function. Unlike Fourier transform whose basis functions are sinusoids, wavelet transforms are based on small waves called wavelets of limited duration. Fourier transform provides only frequency information, but wavelet transform provides time frequency information. Wavelet leads to a multi-resolution analysis of signals. Multi-resolution analysis, that is a representation of a signal, example on images in more than one resolution per scale. Features that might go undetected at one resolution may easy to spot in another. This is a multi-resolution image, a natural image, and its local histogram variations. Local histogram variations. Small objects are viewed at high resolutions. Large objects require only a coarse resolution. Images have locally varying statistics, resulting in combination of edges, abrupt features, and homogeneous regions. Image pyramids. You can see an image pyramid. This is level 0, level 1, level 2, etc. Level J minus 1, level G, base, n cross n by 2 cross n by 2, 4 cross 2, 2 cross 2, I cross 1. Image pyramid is the simple structure for representing images at more than one resolution. An image pyramid is a collection of decreasing resolution images arranged in the shape of a pyramid. It is devised for machine vision and image compression algorithms. The base of pyramid contains a high resolution Base of pyramid contains a high resolution representation of image being processed. The apex contains, the base contains high resolution, the apex contains low resolution approximation. As we move up the pyramid, both size and resolution decreases. Both size as well as resolution decreases. See here N by N, and here N by 2 into N by 2, N by 4 into N by 4. Like that, it decreases. Prediction residual pyramid. At each resolution level, the prediction error is retained along with lowest resolution level image. The original image may be reconstructed from this information. You can see here the downsampler, row and columns, approximation filter, level J output image. This is level J minus 1 approximation. This is upsampler rows and column, interpolation filter, prediction, level G prediction, residual. Level J input image. Base level J is of size 2 to the power of J into 2 to the power of J, or n cross n, where J is equal to log n to the base 2. Apex level 0 is of size 1 cross 1, and general level J is of size 2 to the power of J into 2 to the power of J, where J is in between 0 and J. The image pyramid is shown composed of J plus 1 resolution levels from 2 to the power of J to 2, from 2 to the power of J into 2 to the power of J to 2 to the power of 0 into 2 to the power of 0. Most image pyramids are truncated to P plus 1 levels, where P is in between 1 and J. J is equal to J minus P, J minus etc. J minus 2, J minus 1, comma J. The total number of pixels in a P plus 1 level pyramid for P greater than 0 is n square into 1 plus 1 by 4 to the power of 1 plus 1 by 4 square plus etc. 1 by 4 to the power of P less than or equal to 4 by 3 into n square. System for creating image pyramids. A pyramidal image structure and system block diagram for creating it. This is a system block diagram for creating this image pyramid. Image pyramid. During the first iteration, the original image 2 cross j into 2 cross j to the power of j cross 2 to the power of j image is applied as the input image. This produces the level j minus 1 approximate and level j prediction residual results. For iteration, j is equal to j minus 1, j minus 2, etc. j minus p plus 1. The previous iteration's level j minus 1 approximation output is used as the input. At each level, we have approximation image and a residual image. The original image, which is at the base of the pyramid, and its p approximation from the approximation pyramid. The residual outputs from a residual pyramid. Approximation residual pyramids are computed in an iterative fashion. A P plus 1 level pyramid is built by executing the operation in the block diagram P times. During the first iteration, the original 2 cross 2 to the power j into 2 to the power j image is applied as the input image. This produces the level j minus 1 approximate and level j prediction residual results. For iteration, j is equal to j minus 1, j minus 2, etc. j minus p plus 1. The previous iteration's levels j minus 1 approximation output is used as the input. Each iteration is composed of 3 sequential steps. Compute a reduced resolution approximation of the input image. This is done by filtering the input and downsamplings, that is subsampling the filter result by a factor of 2. Filter neighborhood averaging, partial filtering. The quality of the generated approximation is a function of the filter selected. Upsample output of a previous step by a factor of 2 and filter the result. This creates a prediction image with the same resolution as the input. By interpolating the intensities between the pixels of step 1, the interpolation filter determines how accurately the prediction approximates the input to step 1. Compute the difference between the prediction of step 2 and the input to step 1. The difference can be later used to reconstruct progressively the original images. You can see from the diagram two image pyramids and their statistics, a Gaussian pyramid and a Laplacian prediction. That is prediction residual. We will go for multiple choice questions. The shifted waveform of the given input waveform is B. Wavelets led to a dash analysis of signals. Multi-resolution analysis of signals. Small objects are viewed at high resolutions. True. Approximation residual pyramids are computed in an iterative fashion. True. The quality of the generated approximation is a function of the filter selected. True. These are the references. And thank you. We'll stop the session here.